Thank you for the kind introduction. Hi, everyone. This is Xinfeng from Meta. I'm glad to see over the last couple of days, many research work has been using the Llama as the evaluation. And in today's talk, we're going to share our work on scaling the Llama training with the efficient parallelism strategies. And I'm presenting on behalf of the team. Okay. Llama 3 hurdle models is a collection of pre-trained instruction-tuned models. And it contains a various kind of model size, modalities, and context lengths. Specifically in the Llama 3.1, we have a model has parameters up to 405B model parameters. And it was pre-trained up to 128K context length. In the Llama 3.2, we have models cover the different input modalities, including taking the image as the input. To deliver and ship these models to the world as soon as possible, we pre-trained these models up on 16,000 GPUs. In today's talk, we are going to focus on the parallelism, which is a key pillar that scales the whole system into 16,000 GPUs. Here's a quick agenda. We'll quickly go over the introduction to the parallelism and deep dive into the pipeline parallelism and context parallelism, the design we use in the Llama training system. And finally, we'll share how we put this together into the whole system. Let's get a quick intro into the parallelism. So parallelism refers to the parallel algorithm that we partition split the input and model parameters across the GPUs. And I would like to demonstrate how the 4D parallelism works, starting from an example of training the model on a single GPU. Here's an example of a training step that takes an input batch of 16 tokens and passes it to a model of 4 layers. The first kind of parallelism that splits the input batch is called the data parallelism. It's split along the data batch dimension, and every DP rank gets its own input batch for the training step. Logically, all the model parameters are duplicated across the DP ranks, and they need to all reduce the gradient of parameters at the end of the training step to ensure a consistent and identical view of model parameters at the beginning of the next training step. The next kind of parallelism that also split the input data is a context parallelism. But different from the data parallelism that split along the batch size dimension, the context parallelism split along the sequence length dimension, and every CP ranks get a portion of the input sequences. Other than splitting the input data batch, we can also split the model parameters. Pipeline parallelism splits along the layer IDs on the model parameters. It also splits the input across the into micro batches and pass these micro batches into the model layers to run a forward and backward schedule in a pipeline manner. That's so-called pipeline parallelism. And we can also split along the model dimensions this is called the tensor parallelism, and every TP rank gets a shard of the layer parameters they need to communicate with each other of the intermediate result during the forward and backward computation. All of these put together is a 4D parallelism, and any GPU in such a 4D parallelism system that needs to process a part of the input tokens. For example, the GPU with the DP rank ID 1, CP rank ID 0, PP rank ID 0 and TP rank ID 1 need to process the input tokens covered by the gray block as shown in this figure. And it also holds a shadow of the model parameters that covered by the gray block at the right-hand side of this figure. Our work is trying to come up with the 4D parallelism that's scaling it into 16,000 GPUs. There are many challenges that when we are designing such a system. The first challenge is that we need to deliver a very good performance and memory efficiency. Meanwhile, flexibility is equally important because along the training of Llama 3 hurdle models, there are different input model configurations, such as the training multimodal and non-context phase of the models. And we also need to deal with the very different and input-dependent dynamic attention mask. Finally, we also need to figure out some operational complexity and address the challenges over layer, especially how we debug the efficiency and numerics at scale for this system. We're going to deep dive into our designs and also how we address all of these challenges. Let's start with some pipeline parallelism. Back to 2 years ago when we started the Llama 3 project, there are two kind of existing pipeline parallelisms. One is called the 1F1B, the other is OF-OB. The F stands for a forward of a microbatch, the B stands for a backward of a microbatch. As shown in this figure, the 1F1B schedule tries to minimize the number of microbatches in the warm-up phase, and during a steady 1F1B phase, the pipeline schedule runs forward and backward in an interleaved manner so that it minimizes the memory consumption on the activation part. While comparing with the 1F1B schedule, OF-OB exhausted the forward of all the microbatches. In this way, although it increases the memory usage, but it provides a better overlapping of the point-to-point communication with the pipeline forward and backward computation. Different from the 1F1B and OF-OB schedule, our Llama 3 pipeline parallelism schedule is a unify of these two and generalize them into a flexible number of microbatches used in the warm-up. Such a capability that allows us to explore all the possible design space to figure out an optimal combo between the performance and memory efficiency. When we need a better memory efficiency, we lean towards a 1F1B by reducing the number of microbatches in the warm-up phase. And if we need a better performance while allows a larger memory consumption, we can lean towards the OF-OB by increasing the number of microbatches in the warm-up phase. In addition to the efficiency, flexibility is equally important in the pipeline parallelism design. In the Llama, we often need to deal with different input batch size and the model configurations during the training. Original 1F1B has a limitation on the batch size with respect to the pipeline parallelism size. Meanwhile, we also need to deal with a pretty heterogeneous model architecture, especially the multimodality. The right-hand side picture shows our multimodality model architecture, which takes an input of the image, pass it to the image encoder to generate the image tokens, pass it to the cross-attention layer blocks. This extra block of the image encoder could introduce a pipeline imbalance if we have a linear layer placement of the pipeline parallelism. To address this challenge, we leverage our flexible pipeline parallelism schedule a bit to allow us to adjust the number of microbatches in the warm-up phase, and so that we can insert the extra number of microbatches in the original bubble place of the 1F1B. This allows us to pass any batch size into the pipeline parallelism while maintaining a good memory efficiency. And to address the challenge of the heterogeneous model architecture, we duplicate the image encoders across the different pipeline stages and process the input images in parallel and all get the input image tokens before the beginning of the pipeline schedule. Although this introduces more memory overheads, but it allows us to boost the pipeline parallelism efficiency while in parallel processing the input images. We also customize our own context parallelism design in the Llama 3 4D parallelism. Let's do a quick recap along the context parallelism. The data parallelism split the input batch along the batch size dimension, while the context parallelism split on the sequence length dimension. Here's an example of a data parallel of 4 ranks versus a data parallel of 2 ranks and a context parallel of 2 ranks. And we can see that the case enabling the context parallelism has a larger batch size, but smaller sequence length. While the context parallelism helps the pipeline parallelism's efficiency, especially during the 1F1B phase, the larger batch size in the PP schedule does not mean a more memory consumption because a larger batch size means a longer 1F1B phase. While the smaller sequence length can help us reduce the peak memory usage. And as a result, when we are using the context parallelism together with the pipeline parallelism, it helps with the system memory efficiency. However, we also have the flexibility challenges for the context parallelism. So in the Llama 3, specifically, we use a document mask other than a normal full causal mask. As shown in this example, a full causal mask that asks every token in the input sequence to attend all its prior token in the input training sequence. However, the document mask restricts the attention into the tokens from the same training document. And this input training document is input dependent. Thus, this attention mask can change dynamically with the training process. Our solution is an all-gather-based CP attention to address this flexibility challenge. The solution all gathers the KV tensors at the beginning of the CP attention computation, and it's easy to program the attention mask because every local queue trunk of the tokens have a global view of all the KV tokens. However, it exposes the communication latency in the all-gather. In Llama 3 training, this is not the system bottlenecks mainly for two reasons. First, we use a group query attention where the KV tensor is much smaller than the Q tensor. And secondly, if we think of the problem in a time complexity and scalability manner, the time we spend on the computation as the time complexity spent on the computation is a square to the sequence length, while the time complexity of the communication is linear to the sequence length. When the sequence length increases, the ratio of the elapsed time spent on the communication decreases. Finally, let's demonstrate how we put all these things together in the 4D parallelism. When we put all of these parallelisms together, the order of these parallelisms and the size of them affect the efficiency significantly. In the Llama 3 training, we order the parallelism in the order of the tensor parallelism, context parallelism, pipeline parallelism, and data parallelism. This represents a decreasing order of the communication traffic. We want the most communication intensive layer of the parallelism can fully utilize the network bandwidth, the innermost layer of the network hierarchy, especially the NVLink across the GPU within the node. And when we decide the size of the different parallelism, we need to have a model parallelism TP and PP to be large enough so that we can fit the training job into a limited memory capacity of the GPU. And we need the data parallelism, pipeline parallelism together be smaller than the global batch size. So both of them split on the batch size dimension. When considering all these constraints, we come up with the design space and figure out the optimal combination to deliver the best performance. We also have several operational complexity and challenges when dealing with this system at scale. The first problem is how to debug the efficiency of this system at scale. When look at the performance trace, usually it's difficult to identify the slowness rank and bottleneck in the system. For example, this figure shows a profiling trace of a tensor parallelism group of 4 ranks. From this figure, we might say that the rank 2 is the slowest one in the system. However, due to the synchronous nature of the parallelism, the slowness could come from a slow rank 6 in the same context parallelism. Internally, we need to have a profiling tool that helps us analyze the propagation of this slowness to identify and root cause the issue. Another tricky part is the numerics. Ideally, the context parallelism does not change the output of the training. However, the floating point is not associative nor commutative, especially when we are using 16-bit floating point computation. Here's an example that when we try to accumulate the gradient of the parameters in the pipeline parallelism from 2 micro batches, they are not the same as passing the whole input batch into the forward and backward. So internally, to figure out the places we need a high precision accumulation, we often need to serialize the parallel computation of the different parallelism to figure out the places that reduce the impact on the numerics when applying the parallelism. Finally, I would like to share with you some of the evaluation results. When we put all these parallelism together and run it on 16,000 GPUs, our system delivers up to 400 teraflops per second on H100 in BF16 computation. Even for the long context phase training on 128K sequence length, our system can still deliver up to 380 teraflops per second. Considering the hardware peak of H100 as around 990 teraflops per second, our system utilized the H100 compute capability around 40%. And I would like also to present a further deep dive of the computation time analysis in a tester job of AK GPU. And as you can see from this figure, all the GPUs like, spend pretty different time in the computation due to the imbalanced workloads introduced by the document mask we mentioned previously. And due to the nature of the synchronous computing in the parallelism, this leaves up to a room of further 15% performance improvement of the end-to-end job. In the upcoming OSDI next month in Boston, we'll share our solution on designing a workload-balanced faulty parallelism to address the challenge of this imbalance in the system scale. Finally, before concluding today's talk, I would like to share some of our observations and recommendations towards the future hardware, especially the training large language model. There are several observations and recommendations we made in our paper, but there's one I would specifically like to share with the community. It's about the CPU. Yes, we spend most of time today talking about the GPU computation and synchronization. Very surprisingly, in the hyperscale training, CPU may become the bottleneck. So if we think of the problem as like dividing the workloads across this GPU, the flops per GPU decrease with the number of GPU, because like the total workloads depends on the model configuration and the training jobs. Well, when we add more GPUs into the system, each GPU gets a smaller workload. Unfortunately, the overhead to launch a GPU kernel does not decrease because the number of kernels usually remains the same when we add a number of more GPUs into the system. This is problematic when we run into thousands of the GPU, and when the GPU kernel becomes smaller, the CPU could become the bottleneck of the system. Here's a quick summary of today's talk. Today we talk about the parallelism, our parallelism solution to deliver an efficient and flexible faulty parallelism solution at scale, and we demonstrated some of operational complexity and our lessons on that. In the ongoing Llama 4 projects, we are delivering a system at a bigger scale that can scale up to hundreds of thousands of GPU, and we are extending the parallelism into more dimension to support the MOE model, and exploring the low and mixed precision training to deliver a better end-to-end performance. And we look forward to share more about the Llama 4 parallelism with the community. Last but not least, thank you for your attention.